Okay, day 30 in our last section, 6.3. Still looking at systems of equations, but we're going to be introducing the use of matrices to help solve them. So if we look at this system, here it's just a linear system. But if we think back to solving division problems using synthetic division, in synthetic division, we set it up and ignored the variables. We just used the coefficients. In a similar way, when we solve a system using matrices, we're going to ignore the variables. We're going to let those variables be controlled by the placement in our matrix. So a matrix, in this case, is going to look something like this. We have 4x, so we're going to take the coefficient and just put a 4. We have our positive 2y, so we're going to take that as our second value, and then we have our negative 3. Now I'm going to leave a little more space there with that, and then here our coefficient of x is 1, not 0. Make sure it's 1. 5y, so we've got a positive 5, and we have a negative 4. And so there is our matrix. Now we could put sometimes they put a vertical line here to separate and show that these values here are the coefficients of our variables, and these are our constants, which are our solutions on the other side of our equal sign. But let's talk about some terminology here with matrix. So, any rectangular array of numbers, as this, is called a matrix, and if we have more than one, we have matrices. This matrix happens to be what we call an augmented matrix because it contains not just the coefficients, which are these values, but it also contains our constants, what our values are on the other side of the equation. In most cases, we won't show the line, but it's helpful maybe initially to recognize that that separates our coefficients from our constants here. If we look at just this portion of it, the 4, 2, 1, 5, that's our coefficient matrix because those are just the coefficients of our original system. The rows are horizontal, columns are vertical. So in this case, we have 2 rows and we have 3 columns. Okay? One of the things that's very important here is that when we talk about the order of a matrix, we always list rows first and then columns. So this is it's an m by n matrix, where m represents the number of rows and then the number of columns. Okay. If those two values are equal, then we have a square matrix. So we can do the same thing with these rows that we did with our normal Gaussian elimination, only we're just doing it with matrices. So we can interchange any 2 rows. We can multiply each row or each entry in a row by the same non-zero constant, and we can add 2 rows, one row to the other row to get a new equivalent row. Okay? So we can use those operations on an augmented matrix to solve the system. So suppose we have, here is a system that we basically would consider in the form solved for us, not completely, but in the form that we are looking to achieve. So the question we ask is, what would this look like if we were to put this, express it as an augmented matrix? So we use these brackets here to indicate a matrix. And we're just going to put in our coefficients. So we have 1, negative 2, positive 3, negative 2. And then our next row, well, we don't have any x's, so we have to include a 0. And then coefficient of y is 1. Coefficient of z is negative 2 and 2. And finally, our third row, well, there's 2 zeros in there. So we end up with 0, 0, 1, 3. So there is our system represented as an augmented matrix. And so this is a form that we would like to basically achieve with our matrix as we are working towards the goal. And this is the kind of goal that we want. We want to end up with these zeros here in this situation. So let's take a look at an example. So if we're going to solve this system using matrices, let's start by representing the matrix. So we'll just go over here. So we have 2, negative 1, 4, negative 3, 1, negative 2, negative 10, negative 6, and 3 for x. But notice that it goes from x to z. There is no y, so we have to put a 0 in for y. And then we have 4 and 7. So here is our initial matrix. And our goal is to try to get these zeros in these three, basically, come back here, we're trying to get these 3 slots all to be zeros for us. So, and we would like to have 1s here, so therefore let's go ahead and make it simple and swap row 2 with row 1. And so our new matrix is going to be 1, negative 2, negative 10, negative 6, and 2, negative 1, 4, negative 3, and this row stays the same, 3, 0, 4, 7. Okay, so we just swapped rows 1 and 2. Now we're going to multiply row 1. Let's multiply row 1 by negative 2. Because we're going to try to combine it with this one and make that a 0. So that's going to give me a negative 2, positive 4, positive 20, and positive 12. And here we have, everything stays the same, 2, negative 1, 4, negative 3. And I'm not doing anything with row 3, so we're just going to indicate that that's not going to change. So therefore, I multiplied row 1 by negative 2 to get this. Now I'm going to add these and replace row 2 with the values. So let me see if I can squeeze this in here. So if I add negative 2 plus 2, I'm going to end up with a 0. 4 plus negative 1, I get 3. 20 plus 4 is 24. And 12 plus negative 3 is 9. Okay. I'm going to go back to row 1 and leave it the way it was initially, which is a 1, negative 2, negative 10, negative 6. And I have our row 3, which we're not going to change yet. 0, 3, 4, 7. Okay. So now I need to turn this spot into a 0. So I'm going to multiply row 1 again row 1 times negative 3. So I'm going to show negative 3 multiplied times row 1 is going to give me now a negative 3, a positive 6, a positive 30, a positive 18. Row 2 now, we're just going to leave it as it is, so I'm not going to even rewrite it. Row 3 is going to stay the same, so 3, 0, 4, 7. And so I'm now going to add row 1 to row 3 and place it in row 3. So that means I'm going to get a 0 here. 6 plus 0 introduces a 6 here. And then we've got, what, 34 and 25. Row 1, we're going back to our original row 1, 1, negative 2, negative 10, negative 6. And we're going to insert our row 2 that we got from over here, which is a 0, 3, 24, and 9. So now we're almost there. We got 2 of our zeros. I have 1 0 left to achieve. So I can do that if I multiply row 2 by negative 2. So I'm going to take this row 2 times negative 2. And here row 1 is not involved in our problem, so we'll just line that out. Row 2 is going to be 0, negative 6, negative 48, and negative 18. Row 3 is our 0, 6, 34, 25, and we're going to add those two. So now go back to inserting our normal 1, row 1. So 1, negative 2, negative 10, negative 6, and then we have row 2, which is 0, 3, 24, 9. And now we're adding these two. I should have added that first probably. But I'm going to get a 0, 0, and negative 48 plus 34 is going to give me a negative, what, 14. And we end up with positive 7. Okay? So there I have achieved my goal of getting my 3 zeros there, that we could now go ahead and solve it from this point on. So what that means, if we translate this over here, if we look at the bottom equation, let's change colors here. So we look at this, that leaves us with negative 14z equals 7. So if I divide both sides by negative 14, I get z is equal to a negative 1/2. So then I can take that and plug it in here. So now I have 3y plus 24 times negative 1/2 now, for my z, equals 9. I end up with 3y minus 12 equals 9. And so 3y, add 12 to both sides, equals 21. So y is equal to 7. And finally, I can plug that back into my very first equation, where I have x minus 2 times y, which is 7, minus 10 times z, which is a negative 1/2, equals negative 6. got x minus 14, negative times a negative is a positive 5, equals negative 6. So negative 14 plus 5 is negative 9. Add 9 to both sides, we get x equals 3. Okay, so therefore we're claiming that our solution is going to be 3, 7, negative 1/2. So you might be thinking, what is the advantage of using matrices? Obviously a little bit without having to write your x, y, and z. But it's not a huge advantage over what we've seen before. Well, the advantage comes in the fact that we can take these matrices and solve them using our calculators. So take out your calculator, and we're going to solve the same system now and see how it works on a calculator. So here's my calculator. Our first thing is we have to enter our matrix. So we're going to go second and the inverse x matrix. Now these are just names of matrices, and what we're going to do is we have to come over and enter our matrix into, in this case, matrix A. Notice that your calculator names a matrix with the square brackets around it. It's not something that you can type in from the keyboard. You have to come here to pull up a matrix name. Anyway, so we're going to edit this, so we're going to hit enter. And our matrix, the dimensions again were a 3 by 4. So go 3 by 4. It gives us our 3 rows and 4 columns. And now we're ready for input. So we have in cell 1-1 of our matrix A, we're ready to put our values. So we're going to do 2, negative 1. Make sure you use the negative, not the minus 1. And we had 4, negative 3. Okay, second row. Notice how the subscripting is used here. So matrix A, subscript 2, 1. So row 2, column 1 is the next element. And so that's going to be a 1, negative 2, negative 10, negative 6. And then our third row, first column, is 3, 0, and 4, 7. Okay, so go back, quit, go back to our menu. So here, just to show you that what we have in matrix A, if I go second matrix and call up the name A, now it's a 3 by 4, we know, and I just hit enter, and there it shows my matrix values. So we're going to go through the same kind of steps that we did before by hand, but rather than doing it by hand, we're going to do it on the calculator. So it's going to, our first thing would be to swap this row, row 2, with row 1. So to make that happen, we're going to go second, matrix, we're going to come over to math, and now it's at the very bottom, so I'm going to use the up arrow to go to the very bottom, and I want to do this C, row swap. So I've got up to row swap. And so we're going to have to indicate, well, what matrix are we using? So second matrix A is the name, comma, and then what rows do we want to swap? Well, row 1 and row 2 need to get swapped for matrix A. Now, if you just did this by itself, it would swap those, but watch what happens. It shows them swapped. But if I recall matrix A, and I print it, matrix A is exactly the same way it was initially. The rows aren't swapped. So what you have to remember to do is we want to store our operation. After we're done, we have to store it back into matrix A. So it's going to look something like this. Second matrix, we're going to come over here and we're going to go swap. That's matrix A. Row 1 with row 2. And now we're going to store, so we have to use this, the STO button with the arrow. So hit store, and we want to store it back into matrix A when we're finished. So now when I hit enter, there is my row substitution. But now if I type in row A, let's just double check this, and I call up matrix A, notice it has converted to this. It has maintained this exchange. Okay, so now we need to, our goal here is to get zeros here, here, and here. So to make this a 0, I need to multiply row 1 by a -2 and add it. Now the thing is, we can do all of that in one maneuver here. So if I go second matrix, come over here to math and do an up arrow, notice the bottom one says we're going to multiply times a row and then we're going to add it to something. So that's what we want to do here. So we have to say what we're going to multiply by. So I want to multiply row 1 by -2, and then I have to tell it what matrix we're talking about. So second matrix A, and then I need to tell it what row am I going to be multiplying. So -2 times matrix A with what row? Well, we're going to multiply it times row 1, and we're going to add that to row 2. But again, don't forget, I need to go a store and store that back into matrix A. So now I have accomplished what I wanted. Here was my previous values. I wanted to make this a 0, so I multiplied row 1 by -2 and added it. And in doing so, I ended up with this matrix. Notice row 1 hasn't changed permanently. Row 2 is what has been converted. So now I need to convert this to a 0. So we're going to go second matrix. Again, we're going to go times row plus, and we're going to multiply this time row 1 by -3. We're still going to be dealing with matrix A, and we're multiplying -3 times row 1, and we're adding it to row 3 now. And we want to again store that in matrix A. And there we go. We now have got our 0 down here. So we still have to get a 0 here, but because that's row 2 has a 3 there, I can accomplish what we did by hand. Again, by doing second matrix, okay, and we're going to multiply by -2 times matrix A. So we're multiplying -2 times row 2. and we're going to add it to row 3. Now, suppose that you make a mistake and you forget to store that. So let's just see what happens if I forget to store that. I hit enter, and I've done it, and then I realize, oh, wait a second, I didn't store this. So matrix A is going to be the same as what was back up here. But I can take this and say, oh wait, I want that previous answer. Okay, if I just hit second answer, I want that stored back in matrix A. I will now have maintained it without having to recalculate it or redo it. So there I have achieved my Gaussian elimination format that we did, and then from there we can go ahead and enter and solve it by hand from there. Okay? So we have basically achieved this matrix there, and we can go through these steps to solve and get back to our solution here. Okay? So here's an example for you to try. Try to set up and solve the following system using matrices. So don't worry about trying to do it by hand, but use your calculator and go through the steps on your own and see if you can produce a matrix that's going to be in the form here of 1 with 0, 0, and 0 here. And I don't know what these values will be, but anyway. So you end up with a matrix that looks something like this on your calculator that you can solve. And we'll pick up from here tomorrow and look at some additional work that can be done with this. Good luck.